Hey, welcome back. So I've been in Scotland for 5 weeks on vacation, and it's a gorgeous country. It was beautiful. So perfect vacation, to be honest. Now that I'm back, I would like to talk about this Nikon measuring microscope. I mentioned to a friend that I'm looking for a measuring microscope, a bigger measuring microscope, very, very low key. Not really a pressing need, but nice to have. And a few days later, Sam hooked me up with this thing. There is a whole backstory to it, but Sam picked it up, dropped it off here, and made a stinking good deal for me with this microscope. So thanks, Sam. You absolutely didn't have to do this, but I appreciate it a lot, and thank you so much. So what this is a Nikon MM-40 with a 03L XY table. The XY table has a travel of 50 by 100 millimeters and integral 0.5 micron linear scales. It also came with a quadra-check DRO and an external light source for a fiber optic ring light. So it was really spec'd out very well by whoever bought this in the first place. You can still purchase the Nikon MM series new, and they are horrendous expensive. It's very easy to drop 5 figures on one of these, and it goes up very far in their pricing. So if you spec them out, you can easily drop 40,000 euros on. This was way less. This was absurdly cheap in the end. It was in decent condition. The optical elements all look good. The mechanical frame also is in good nick. I didn't see any damage. The only physical damage or mechanical damage was a bent lead screw in the x-axis, but that's a very easy part to make. Since there is no real precision required, all the precision comes from the linear scales. The lead screw is just there to move the stage around. So it's a very easy lathe part. Well, not super easy because it's long and slender, but we will look into that later. I need to take it apart and clean it. It had been very dirty. It looked like it had been used in something like a grinding shop. It was covered in a gooey, dried coolant residue and what felt like grinding dust. So taking it apart and cleaning all the components was mandatory. Here's the entire setup. We have the microscope, we have the cross slide. I'm mentioning the cross slide separately because you purchase these two items individually and put them together as you need it. I have the quadra-check digital readout, and I have a light source up here for the ring light, which goes around the lens. There is a second light source behind this tube here. This tube is for adding a camera on top. This light source projects light directly into the optical path of the microscope. So there is light coming out of the lens and illuminating the object that you're inspecting from above. And then there is lastly a light source back here, which projects light from underneath the glass table here. I will show that all in detail later. The cross slide has linear scales in Y and X, and those linear scales do not read in 5 microns. They don't read in 1 micron. They read in half a micron per division. If you look at the digital readout, there are 4 digits behind the decimal point, and yeah, it's reading half a micron. Now that's quite impressive. The first thing that I want to deal with is the table up here. This can move side to side by means of opening the half nut or by using this hand crank. And as you can see, there is some serious wobble to it, which is frankly quite annoying. The y-axis also has only a hand crank, no half nut, but that's plenty fine. These are the cables and the connectors for the linear scales. I already rebuilt those connectors. The cables were frayed, the insulation on the ends was all broken up and crusty, so I cleaned the entire cable and redid all the internal connections, so these are now reliable again. This is the glass. Oh, by the way, I do not only have the flat table here, it also came with this low profile rotary table, which can be mounted on top and allows for arc minute adjustment of whatever you have here on the table, which is quite a nice feature. The glass in here needs to be replaced. This is all scratched up, and I will probably also replace this piece of glass down here. Don't worry, I will show the rotary table in detail. So this is the glass. Normally there is a cover over the half nut like this, but I already removed this because I wanted to see the damage on the lead screw. I think this retains the lower green filter glass. Blink. Oh! I stand corrected. This is an entire assembly with a mirror, 45-degree mirror. And just a glass lens, I guess. Oh yeah, the green light comes from the light source itself. It has a color filter. I turned it around and took the rear cover off because I wanted to see the counterweight. But there is no counterweight. It's a little bit more scary. This is a large, like a coiled spring you would find in a coil of a milling machine. And this is just hanging on by those two steel cables and counteracting the weight of the head. You can see it unroll down here. And when I say it's scary, well, it's not really scary until you start to take it apart and it flings in your face. Apart from that, that's a perfectly serviceable solution. I like it. Has the advantage of, if you start to move it around, for example, if you put it on a truck and move it somewhere else, you don't have to secure the counterweight. It doesn't bounce around in the column. Like on a tree moss height gauge, there is a large free-floating and suspended counterweight in the column. And you have to secure that when you start to carry it in a car or something like that. So maybe that's the reason why they went with a spring solution here. But I'm not going to take this apart because this appears to be working just fine. With the microscope mostly in a functional and cleaned up condition, it's time to focus on the XY table. And I'm not entirely sure how to go about this. This long lead screw here poses a bit of a problem. A fairly long piece to be remachined, but also it seems to be kinked in multiple points, so straightening it out will be a royal nightmare. So we will see how we're going about that. Also, I need to be careful with the linear scales in here. Let's take the cover off so you see what I'm talking about. Because the glass scales in here are open frame design. So that's a piece of glass with the grading etched onto it. Well, it's metal deposited onto the glass and then etched. Here's a close-up of what we're dealing with. This is the glass strip with the graduation on there, and this is the reed head. I guess here in the center is where the photodiode and the light source on the other side are. And we have 3 roller bearings on this side. There is one fixed that's mounted to the frame of the reed head, and 2 roller bearings that are mounted on these leaf springs to put pressure on the glass scale. So this runs smooth but still allows for a little bit of compliance. I would like to take this off to get it all cleaned up. But also I would like to not damage the 1/2 micron gas scales. Grab yourself a chair. This will take some time. Let's move this over the table so I can reach the mounting screws from underneath. And see how we can take this apart without causing any damage. So the reed head appears to be mounted from the underside, and the glass scale appears to be only held in place by these 2 blocks down here. I will move the camera down in a second. So I guess by loosening these, okay. So I think the safest way to do this is to loosen these blocks, which seem to pinch the glass strip in here. They have a little bit of rubber on their top side, so they don't crack the glass. And there we go. That just loosened the glass strip. I would like to keep the glass strip and everything in one assembly. There's a clamp for the cable down here. I think when I undo these screws down here, I should be able to take the reed head with the glass off and finagle it around this clamp here. I should do the finagling first before I have the linear scale loose hanging by the wires. There we go. I think I found a way to take it apart. Maybe not the correct way, but a way. There is a PCB on the back side here, which I guess is the signal, something to do with the signal of the linear scale. And there is a connector here. That's the y-axis linear scale. I can just push the cable back here. And then pull it out underneath the axis. And now I should be able to remove the entire linear scale reed head and glass scale component as one piece. Let's take a screwdriver that fits actually. Doink. Let's see. So much for keeping it together. Okay, that's the linear scale taken out of the y-axis. Next we'll do the same in the x-axis. Okay, let's go to the back side. It should be a little bit easier in regards of the cable routing. Oh, and this linear scale is also way cleaner than the y-axis scale. Undo these mounting blocks. The glass scale is really just pinched in there. Let's push this a little bit back. There we go. There's not a lot of talking going on right now because I'm trying to figure out myself what's happening here. So not much I can tell you. But for the moment I'm trying to get the PCB out through the cross table before I proceed any mechanical disassembly. There we go. The PCB comes out to the underside. We'll have a look at that later, doing a Dave Jones style close-up of the PCB, of which I know nothing. What I know is mechanics, and all that's left here is now purely a mechanical system. It's linear guides and drive spindles. So this is way more in my wheelhouse. I think I'm going to take off the x-axis lead screw and half nut assembly, if I find the correct wrench. So this is I feel way more comfortable doing this than dealing with the linear scales and electronics. Also got me some recommendations from Silo's Garage and Sam on cleaning the glass scales. There we go, that's the half nut and screw assembly. We'll take that apart separately. Okay, there is the y-axis lead screw. There is a second screw hidden under the y-axis slide here. Oops! The y-axis is, by the way, spring-loaded for backlash, dealing with the backlash. There we go, we can finagle this out. And let's see if we can get the spring out there. When I undo the screw, it will fling away. So I have to hold it in place. Get the screw out, and then grab the spring and untension it. I removed the covers on the end of the linear rails, and I think if I take out these screws, which prevent, well, these hold the hardened strips onto the casting. The balls run on spring steel strips, because this is just a casting, this is soft. So they inlaid some strips here, which appears to be spring steel. And these screws not only hold the strips in place, which is a super primitive solution, but very effective, but also prevent the balls to run out the end of the guideway. Put 2 trays underneath under each of one of the slideways, so when I pull this off, I don't lose all of the ball-bearing balls. Doink. Let's lay less balls than I expected. That's 4 per side. And this strip of sheet metal is the cage that keeps them in alignment. Same deal again in the x-axis. I will leave the linear guides in place. Just going to clean everything and inspect it. I don't expect any wear, otherwise I would have to unbolt these and find somebody with a surface grinder long enough to regrind those. But these are fairly easy to regrind if there is any damage to them. The shorter ones I could do on my own surface grinder. Also, if the spring steel strips have any damage, I will just flip them around to the other side. I think that will be plenty good enough. So, time to clean these parts. This cleans up quite nicely. Little jump forward in time. The x-axis is back together. Everything is cleaned. I put in new balls in the x-axis and I will do the same in the y-axis. I happen to have 7.945 millimeter balls, new ones, from who knows where I got those or for what I got those. But they are the exact diameter that were in the ball slides. The original balls looked a little bit tarnished, so I figured, heck, let's replace them. Also, the screws that hold the spring steel strips in here are JIS profile, very similar to Phillips, but different profile nevertheless. And I happen to have Torx screws with the same head shape, so I'm using those. The thread is a little bit longer, but Nikon was kind enough to draw and tap these holes deep enough so I don't have to shorten screws. X-axis back together. I already mounted the spring in here. When I put the y-axis back on, now I need to install the spring steel strip for the y-axis. It's already in on this side, so let's move over and do this side. It's a little bit easier to do this with the guide assembly standing up vertically. So the way I'm doing this is, putting in the screw. And the way this works is just the 90-degree head of the screw pinching down on the spring steel strip. So these get screwed in almost all the way. I'll make sure. This is stupid with gloves. And we make sure there is no grit or something like that. On the actual mating surfaces, and also we do the usual cleaning of the spring steel strips. We just drop them in here. And yeah, I flipped them around so the wear line, it's just where the blue temper of the spring steel has kind of rolled off. This goes in here. And then we just tighten these screws very lightly so the spring steel strips stay where they should stay. And that's it. That's the installation of the spring steel strips. Super easy. Let's see if we can do a little bit of a helping hand situation here. Oh yeah, this will make things a lot easier. I'm starting on one side, putting in the balls with the cage. You don't see that really very well from your orientation. You will see when I do the same on this side. I just used the bearing balls with some grease, glue them in place, like you would assemble a ball screw. If you ever have done this, you probably know this trick. Now I try to finagle this in. There we go. When I take out the lower blocks, I can drop the guideway in further. There we go. Okay, that was the hardest part. Since the balls have a little bit of preload, you cannot really move the balls or a position in the V-guide. You can bump them a little bit, but it's not the most elegant thing to do. That's what I mean. You can ever so slightly bump them in their lengthwise position. And then at some point you are able to insert the remaining 4 balls in this case on both sides. The Y-axis screw assembly just needed cleaning and it's working perfectly fine. In the long run, I need to remake the nut. It has a little bit of backlash, but since the axis is spring preloaded, there is no noticeable backlash in the hand crank, so it's working perfectly fine. Just greased the lead screw ever so slightly, so it's not running dry, and reassembled it, but now we have to deal with the X-axis screw. That's a little bit more effort. So here's the screw. Already took most of it apart. And here is the half nut, which is this clamp or mousetrap design. It's just 2 leaves that are pushed together via a single spring, closing up on the thread. And to disengage it, you have this lever here with this sheet or with this leaf here. This leaf lives between those 2 parts of the half nut, and when you move the lever, it just spreads those 2 clamshells of the half nut apart. It allows you to move freely along the x-axis. The nut itself seems to be made out of a plastic, well, the half nuts, that is, seem to be made out of plastic. Whoops. And there is also the same abrasive goo in there that we found everywhere else. So while this nut is probably working perfectly fine, I think I would like to remake it, because now that there is all this grit embedded, this wears away on the screw. So that's one problem, the half nut. And the other problem is, of course, the screw. Let me demonstrate. Just rolling it in the jaws of my bench vise tells me what I need to know. So I need to remake this part here. And this will cause some manufacturing troubles, because it's a very long shaft that don't have a follow steady. But I will jerry-rig something together. This is an M8x1 fine thread, right hand. The y-axis is M8x1 left hand. As you can see in the background, things are going back together. I have the PCB already back in the cross slide. Before I tackle the x-axis screw, I want the glass scales back in this and make sure everything is working before I put work into making a new lead screw, of course. So the glass scales worked, but they were super dirty, and to my surprise they still worked and didn't skip numbers. But I figured while I have it apart, getting to clean them. I asked a few friends who are either semiconductor related or actually making glass scales how to clean them without destroying them, and the overall consensus was just to rinse them with isopropyl alcohol, 99.9% grade, and wiping crosswise, because the graduations go this way and you don't want to wipe this way, you want to wipe with the lines. That's at least a consensus. So I'm going to give this a good rinse. I already did this previously. I figured one or two more good rinses won't hurt. Note that I'm resting it on this Kim wipe with the metal side, with the graduation side up, not resting down on the bench. And Sam had a good recommendation. What he does in cases like this, he wets it down with some alcohol. Then he puts a clean room wipe on top of it. Yeah, it looks dirty, but these are clean. And then he pulls the wetted clean room wipe off the item we're cleaning. Then the remaining alcohol is just flashing off. I figured out how the scale goes in. The metal side goes down because the read head, the actual sensor, is also looking from underneath. The light source goes through the glass scale from above. So I think I need to push these brass blocks down. They have a little bit of rubber on their underside, so they don't explode the glass. They just, need to clamp the strip of glass in place. I'm not going to muck with the reed head. I don't know enough about these things. I'm replacing most of the JIS screws with small hex screws. I happen to have nice oxide black ones and some stainless ones that I'm using. So how do we Okay. Before I add all the covers, I will carry this over to the readout and plug it in and see if it works. Plug this little connector back in place. Now we do the same in the y-axis. The glass scales are clean and back in place, and I didn't crack any glass. Reconnected everything, the PCB is in, the connector board on this side is mounted. It's time to try it out. Okay. Okay, moving the y-axis, and that's counting. The x-axis is counting too because there is no screw in it, but as you can see, the x-axis is... Oh, by the way, the travel of this table are officially 100 by 50 millimeters. It can over-travel a little bit. There is a hard stop in both X and Y, so there is no danger of crashing the glass scales. Let's crank this to extreme minus, zero out Y. Move it all the way over. So at least it's counting. So Y is 52. And when I crank back all the way to the hard stop in Y, we should end up at 0 if it doesn't skip any numbers or something like that. But I think these scales have some kind of a check if they miss a mark. Yeah, we're repeating within 0.003 of a millimeter, 3 microns. That's just bumping up against a very crude hard stop in the y-axis. The x-axis stop is kind of similar, so it goes back to 0, and when I move it all the way over to x plus 104.4, going back to 0, should repeat. Yeah, so we're not losing any count here. So that's fine. So yeah, disassembling and cleaning the glass scales didn't produce a whole lot of electronic scrap, which is good. The nightmare you just witnessed is my attempt at mimicking a steady rest without owning a steady rest. So let's get the chips out of the way. So, as I mentioned, I don't own a steady rest. And I don't intend on buying one. I don't have interest in owning one. But for a long and slender part like this feed screw, you need something to support the work very close to where you're cutting, otherwise it starts to vibrate on you like crazy. And I figured I can use some blocks and a piece of phenolic to support the work against the cutter so it doesn't roll off the cutter and start to vibrate. My first idea was to use a shoe like this on the backside. Like sometimes you find something like this on a cylindrical grinder. It doesn't work on a lathe, turns out. Turns out there's a reason why traveling steady rests have their contact point behind and over top that center, so the work doesn't roll out of a, in this case, V. It didn't work at all. It just rolled out and cracked the carbide insert. So I bandsawed this piece of phenolic to mimic a steady rest and clamped it to the 123 block, which is bolted to the cross-slide of my lathe. Means I can't use the cross-slide to adjust my depth of cut, of course, because, well, the steady rest is moving with it. So that means I put the compound to 60 degrees so I can infeed here to get my diameter that I require. And this should be 8 millimeters now. So we have 8.03 here, 8.1 here, and 8.02 here. So it's still deflected in the center quite a bit. And I have to adjust my steady rest now. Means I need to open these two toolmaker clamps. This is one of my gold star setups here. I want to cut as close to the not a steady rest as possible. Okay, to adjust this steady rest, I loosen the toolmaker clamp and I bring my support piece here in contact with the work, press firmly down on it and then tighten these toolmaker clamps. I'm using the toolmaker's clamps over the can twist style of clamps because I can really reef down on these toolmaker's clamps and pinch my support piece here in place. There we go. This seems to work, retracting the tool with the compound, feeding back with the spindle in reverse. Okay, feeding in. Let's give it 0.1 millimeters. Do you notice something? This is the old spindle, that's the new spindle. They're not equal. Turns out this is not 1 millimeter pitch like I eyeballed. It's 1.25 millimeter pitch. And mine is 1 millimeter. That's not a big deal since I want to remake the half nuts anyways, but goes to show I sometimes make very funny mistakes, and this is on the funny side. So let's hacksaw this off and turn the end of the shank to 8 millimeters. So So thanks for sticking around that long. This will be a two-part video. I will show machining the half nut and reassembling the half nut assembly in part 2. Also show the capabilities of a dedicated DRO that's made for measuring compared to a normal mill or lathe DRO. So that will be for part 2. So I hope you enjoyed. Thank you all for watching. Thanks for the support, and I'll be back.